In those terms, it'll be easy to remember. The removal of nitrogen is actually a two-step process. It's simplified. It's a two-step process. The first step is nitrification, and it's by a different group of bacteria, the autotrophic bacteria, which get their carbon source from inorganic carbon, CO2. When it dissolves in the water, it becomes bicarbonate, and that's where they get their carbon source. The second step is converting. In the first step, ammonia gets converted to nitrate. And so that's, you haven't done anything in terms of removal. You've only converted the form. Now you've got nitrate, and you've got to get it to nitrogen gas to be released to the atmosphere. So you're taking it out of solution and trying to put it back into the atmosphere as an inert gas. Those bacteria are the same as the first group. Whoops, went the wrong way. Heterotrophic bacteria, heterotrophic bacteria. Essentially, the bacteria that get a large portion of the bacteria that can break down BOD can also, if you take their oxygen away, breathe with nitrate, and in so doing convert nitrate to nitrogen gas. But the difficulty in doing this is that the heterotrophic bacteria grow so much faster than that second group that if you don't get the concentration of BOD down low enough, the second group can't grow. But the problem is, if you get rid of all of that BOD, you can't do the third step. So, in order for, whoops, sorry. In order for, I'm a better process engineer than I am a gadget guy, so. What did I do? I went the wrong way again. Okay. Bear with me. Okay. So in order for this part to happen, the growth of the autotroph, we've got to get rid of enough BOD to have this happen. But at the same time, when we go to denite, if we get rid of too much BOD, we've got to then add a supplemental carbon source. So the idea is, but if we put it in terms of the biological transformations, and I don't pay too much attention to these overall equations. What I want you to notice, I've color coded. The green is the carbon source. So if we look up here, this equation is BOD removal, but we're using a carbon that's coming in, the raw carbon that's coming into the waste stream. It's already there. That's in green here. If you look at the green in the second equation, the carbon source, as I mentioned, is the inorganic carbon source, the bicarbonate alkalinity. Down here, again, we're looking at an organic carbon source. In this case, this equation is written in terms of biomass degradation. So we've got the carbon sources in each equation, and these two, the carbon sources, are both organic carbon, and this one it's not. Then we've got the form of breathing. In the first case, we've got oxygen, and in the second one, we've got oxygen. The red is how they're breathing, okay, the compound. And in the third one, you see that the nitrate is what these bacteria are using to breathe. And that's kind of one of the major difficulties. In order to get this to occur, you've got to get rid of a lot of this. And then when you go to do this step, you can end up deficient in carbon. So one way to approach this problem, let's talk about some of the organic carbon sources when you're trying to do nitrogen removal. Ideally, what you'd like to be able to do is kind of balance the three reactions so that you can use the carbon that's in the wastewater that's coming in. And if you can do that, then you can avoid paying for additional chemicals downstream, such as methanol or acetate or some of the proprietary chemicals. Now, denitrification has been shown to occur with acetate, ethanol, micro-C, which is one of the proprietary ones. Has anyone heard of micro-C? It's a proprietary agriculturally based carbon source. Methanol has traditionally been the carbon source of choice for a couple of reasons. It's low cost. It's also very low sludge production. The other source of carbon is if the bacteria actually start to break down in the reactor and you get endogenous decay. The carbon that gets released for that, the live bacteria can use. So in order to approach this problem, ideally what you'd like to do is to get your lowest nitrogen value possible by effectively using the carbon that's coming in. So if we look at organic compound or nitrogenous compounds in the wastewater, there's in terms of a typical domestic or municipal type waste, there's really just two forms coming in. Essentially, the organic nitrogen, NH2 minus. Those are the nitrogen molecule, the nitrogens that are attached to these long chain carbonaceous molecules, i.e., what accounts for your BOD. And as the BOD breaks down, the NH2 minus gets released into solution and converts to ammonia. So when you measure your influent nitrogen, what you really want to be looking at is the TKN number, because TKN is equal to all of those organic nitrogen compounds that are associated with the carbonaceous matter and whatever ammonia is there. The next form is ammonia and ammonium, and they're kind of in, you see both forms, and it's dependent on pH. But for the sake of this discussion, we're going to say that what we're seeing is organically bound nitrogen and ammonia as the typical ones in the influent side of things. Now, as the biochemical transformations start to occur, you may start to see nitrite and nitrate. Generally speaking, in a properly functioning nitrification system, the nitrite is so transitory you really don't see it. It's negligible. So the three main compounds, as we start to move through the plant, are ammonia, organic, and nitrate. And as I've already kind of mentioned, this ammonification is essentially that conversion of organic nitrogen, NH2 minus, to ammonia. And it's typically tied in with the rate at which your BOD or your oxidation BOD is occurring. And the significance is that when you're designing or looking at problems in a nitrification system, you need to know that influent TKN number. A lot of times people just focus on the ammonia number. That's only part of the picture. If you have to troubleshoot these systems, you need to know what the load coming in is. So TKN is really the important number when you're designing or troubleshooting. Now, this is just kind of information that I've already talked about. You don't have to remember this. The bacteria, they get their energy, the autotrophic bacteria, the nitrifiers get their energy from the ammonia. And again, as I mentioned, they get their carbon source from an inorganic source. In this case, it's CO2. Now, the key points when you have a nitrification system are that you consume a lot of alkalinity. So when people talk about having to put a nitrogen removal system in, a lot of times you'll hear talk about an alkalinity feed system to make up for potential deficiencies in the influent in terms of alkalinity. Now, a lot of times it's overlooked. People assume that alkalinity is used for the neutralization. A small portion, as I've tried to stress here, is assimilated as a carbon source. The major impact, and this is pretty significant, when you go from a plant, let's say you're trying to upgrade a plant that's just doing BOD and TSS removal, you can see that in order to get rid of 4.3 grams of oxygen per gram of ammonia oxidized, compared with when you're just getting rid of COD or BOD, it's 0.4 grams. It's a tenfold increase. It's a pretty significant increase in cost. Now, one of the things I'm going to highlight later on is you can get some of this back if you can effectively denitrify. Because if you think of oxygen as a chemical, and the fact is that bacteria, some of the bacteria can use either oxygen or nitrate to breathe, that means the nitrate has some value for respiration. And if you effectively get as much denitrification out of that as possible, you can recover some of the energy that you've put in terms of getting rid of the ammonia or converting the ammonia. I'll talk about that more later. Again, this is the equations, and I'm really trying to beat a dead horse here. Bicarbonate alkalinity, and there's a production of the carbonic acid during nitrification. Essentially, this is what you see happening. You've got ammonia and oxygen and bicarbonate in terms of biology and so forth, and then you get a production. This yields biomass, nitrate, and some acid. So the alkalinity issue becomes important because not only are you consuming it for the biomass, but you're also producing acid, so the alkalinity is going to balance. Excess alkalinity that's not assimilated is going to tend to buffer that, the effect of that acid, and keep the pH where it should be. Oh, thought I was just getting used to this. So denitrification is essentially the conversion of nitrate to gaseous nitrogen, and again, it's mediated by heterotrophic bacteria, the same bacteria that get rid of the BOD. And when you do that, you can recover some of the alkalinity that you lost. Remember that previous slide just showed that about 8 milligrams of alkalinity is required for each gram or milligram of ammonia. You can recover about half of that when you denitrify. And again, anoxic conditions are required. This is the equation for that. Oops, went back. Sorry about that. I've already said this. One of the things, okay, respiration essentially is a pathway in which molecular oxygen or some other oxygen serve as an electron acceptor. One thing that I heard in New England a lot, and I want to correct that before it even starts here in Minnesota. The bacteria don't grab the oxygen off of the nitrate. Nitrate's NO3. That's not what happens. What happens is nitrate, when it's in with nitrogen, when in the nitrate form, is in an oxidation state of +5. It has the ability to accept 5 electrons. Essentially, what happens when we breathe, the final process or the ultimate process in respiration for us in bacteria is transfer of electrons. And so, what's happening in denitrification is that bacteria are transferring electrons not to oxygen, but to nitrogen. And it's a stepwise conversion in which that nitrate goes through steps, and the nitrogen picks up an electron with each step. It's a subtlety, but I think it's kind of important. One of the things I mentioned to earlier, if we look at in terms of getting rid of the ammonia, we have 4.7 grams of oxygen. This is in terms of ammonia, not ammonia nitrogen, to oxidize to nitrate. And if we look at the oxidizing equivalent of nitrate, if we take the ratio, if we were to effectively use all of the carbon that's in the wastewater to denitrify, we didn't lose any of that. We were denitrifying as much as all of that nitrate as much as possible. With the incoming organic carbon, we would essentially recover 64 or 62% of the oxygen that we put, the oxygen equivalent of what was put in here. Okay, so if we say, all right, we're feeding so much oxygen to get the ammonia to convert, but what's getting converted, that nitrate, has an oxidizing capability of 2.86 compared to the 4.87, so we can recover it. And it's like a 62% recovery in the oxygen that you've already spent. A lot of times, most people are very familiar with suspended growth systems. Has anybody had any experience running fixed film or biofilm systems? Not too many. Biofilm is another term for fixed film, and essentially what a biofilm is if for example, you left a tennis ball or something floating in a bird bath for a couple of days or a week, and you picked it up in that slime layer underneath, that's a biofilm. And it's really just organic polymer gel that attaches itself to a solid and a solid-liquid interface. And what these biofilm reactors do is essentially put a media in there and run the wastewater over it and develop a biofilm so that the bacteria, unlike the activated sludge system, aren't suspended, but they're fixed in this media. And the colonies that form in these biofilms are actually like little villages. They transfer materials back and forth and so forth. What happens when you're trying to do a system that's going to remove nitrogen, you end up with a biofilm that has the species at different layers. So you remember how I said that we need to get the BOD down to a certain concentration before nitrification can happen? So what happens if we look at, this is a cross-sectional slice of a biofilm. At the very top layers, we've got the heterotrophic bacteria that get rid of BOD. And then as you go deeper, as that as the organic concentration goes down, and you can actually get growth of autotrophic bacteria deeper in. And then deeper still, there's another group of heterotrophic bacteria that can use the nitrate that's being produced, and also any organic carbon that's produced from endogenous decay. So if we take these fundamental theory or fundamental principles of nitrification, and we try, what we want to try to achieve here is to get a system in one reactor that can achieve a low total nitrogen number. 10 seems to be a common number based on the drinking water standards. If you look at a lot of states that have nitrogen numbers, 10 milligrams per liter is the number that they want to see. So how do you do this when you have this kind of dilemma of having to get one thing low enough before the other happens? How do you achieve that in one reactor? And the technology that I'm going to talk about is essentially, we try to do this in a biologically active filter. Essentially, it's a deep bed sand filter. And these types of reactors have two advantages. The media, if it's fine enough, can act as a filter that physically removes material, but it also, if it's small enough, it can provide a very large surface area, so you get a very high biomass concentration, which means a small footprint for your technology. And you don't need downstream solid separation because it's a filter. So the technology that, that we recently got approved in Minnesota is essentially this amphidrome system, which is a deep bed sand filter. And the sand is about 3 millimeters in diameter, and it's got a very high specific surface area, so you end up with very high biomass concentration. I'm going to have to get out of it. I've got a video how this works, but I have to get out of the slideshow in order to make it work. Oh, sorry. In this, I'm sorry. Am I going too fast?
Nope. You got a couple minutes.
This slide is a picture of a simple system in which we have the first tank, which essentially is like a primary clarifier, and then the reactor, and then the final clear well. And I'm going to have to operate this from here.
I can do it.
Oh.
It's taller.
Okay, so what I want to do is just press on these when I tell you.
Okay.
Awesome. Thank you. So in the first part of the system, we have the wastewater flowing into the main tank, or the first tank, and then the supernatant will overflow to the filter. And we're aerating from the bottom up. And the wastewater is flowing down through the sand. And when it goes through the reactor, it actually flows through this pipe, through this pump, which is off during forward flow, and it fills up the clear well. So during this phase, with the air on, we're trying to oxidize BOD and nitrify. So yeah, that's perfect. What happens is every hour, this pump comes on and returns some of the liquid back the same way it came. This check valve closes, it overflows the filter, and then flows back to the anoxic tank. Now the idea is to take some of that treated waste, which is going to have some nitrates in it, bring it back and mix it with the influent wastewater that has organic carbon. So now we want to go to the anoxic cycle. Then what we do is we bring it back through the filter, but with no air. And so now we've got the requisite carbon, because that came in recently. It hasn't gone through under aerobic conditions and been treated. We can now go through the reactor without air and tend to force the reactions toward the denitrification, the third reaction, which requires the organic carbon source. And so this cycles back and forth, and at the end, well, we discharge typically 6 times per day, and most of the systems we've designed to date have been to some sort of a soil absorption field. There have been several surface water discharges, but that's kind of up to what the permit is. So I think, before I exit out of this movie, are there any questions?
There you go. 2 minutes.
2 minutes? All right, that should do it. That's okay. Yeah, no, it was too long. My thing was too long.
I can't imagine why. You know, these process engineers.
Yeah, well, not all of us like to talk, but I do. I don't have a problem talking. Okay. So, this system's been applied for single family up to 200,000 gallons a day. As I mentioned earlier, the biggest one, I think I mentioned it earlier, the biggest one we actually have operating around 100,000 gallons. We have one approved at 200, but it's been held up because of the economy. It can be used in schools, commercial developments, housing. We have one septic receiving facility in Massachusetts. And I think what I'm going to do is skip the controls. Everything's PLC controlled, remote access, it's all standard. I have some performance, but if anyone wants, they can email me and I'll get them anything, and I'll also get them the DEP number, the permit number in the relevant state, so you can actually call the state and get the data without going through me. Not that I manipulated it or anything, but if I were doing it, I would never trust a sales guy. I always tell people, don't trust a guy with too many letters after his name. So this is a 36,000 gallon per day system, and it's dual train. And you can see one of the trains. You can see the covers for the reactors. Generally, these systems are all done underground, and that's actually going to be a real benefit, I think, in Minnesota, because if we insulate the tanks, we go below grade. Concrete doesn't have a high thermal conductivity. This process has been shown to be less affected by ambient temperatures. And that's not to say that the biological reactions aren't affected by temperature. That's not true. That's not what I'm saying. What I'm saying is the way we do this underground is that we're less apt to have problems at colder temperatures. Actually, the first two systems we put in Minnesota, we're actually going to put thermocouples in there to get temperature data for winter operations.
You got about less than a minute, sir.
So here's a system down in the Cape, 20,000 gallons, and any questions?